Wave is basically propagation of energy. Let's keep it very simple. Wave is propagation of energy or momentum. Let's talk about, what is a wave motion. So a wave is a disturbance that transfers energy from one place to another. It does not transfer matter during the energy transfer, right, students? That is what I have shown here. Let's say you imagine a wave like this. That is a shock wave that is caused by earthquake. We call them seismic waves. You are seeing two diagrams here. You would say, why are there two diagrams? Hello students, welcome to your own physics class. Students, today we are beginning with an entirely new unit of physics that is related with waves. And when I say waves, two things that should come to your mind is sound and light. So we will talk about what are waves. We will also discuss how sound operates and how light operates, right? So there are so many new things that you will learn in this unit. It is going to be a big unit, but very exciting, as mostly the things that we will study in this unit, you can clearly relate with them as they are continuously happening around you, and definitely after this you will have a completely different perspective of looking at things, right students? So without wasting any time further, I think we shall start. So put down the heading please. Today we are going to start learning waves. Put down the heading waves and look at these diagrams that I have for you. Just go through them and then we'll discuss what they have to do here. Right students, so the first thing that we are discussing is this pendulum. So very strategically I have placed these diagrams. So first is when I talk about waves. So far your understanding of waves could have been water waves that you see on the beaches, water moving in a particular fashion. That is giving you a feeling of what wave is. So that is why a water wave is something that all my students should be able to relate with, right students? The next thing is this pendulum. So you understand that pendulum keeps oscillating. It doesn't translate. It keeps oscillating about its fixed position. This is its mean position. These are its extreme position. So we can say that pendulum is only oscillating. It is not moving or translating in a big fashion. It is only moving about a fixed position, vibrating about a fixed position. This has a crucial role in understanding waves. You will understand why. Next is of course this, something you can relate with beats or sound. So that is why I have placed, of course this is VibGyor, this is light for you. You have a basic understanding of it because of your thermal physics chapter as well. Then this general diagram of a spring, let's say. So this is also going to give you a feel of what waves are. And then this diagram is also related with waves. But we'll talk about them one by one, students. But the first thing that you need to understand, before even starting with this, is that we will classify either things as matter or as waves. So far we have been discussing matter. We have been discussing an object and we were considering its energy. For example, this pen, when I release this, we were discussing its potential energy, its chemical energy. Maybe you have a light bulb in your room. So that light bulb is basically a particle, right? It is a particle. So things are either particle or they are waves. So what do you mean by waves now? So imagine that light bulb, that is a particle. You can locate that light bulb. Okay, there is this light bulb. But where is the light of that light bulb? So you will say it is spread throughout your room. It does not have a fixed location. That is what waves are. Waves are extended in a whole region. They are not a localized thing that you can identify, okay, this point the wave is. Wave is spread throughout. Now what is a wave is the question. Okay, so let's first break through the basic definition of waves. So very quickly then students, wave is basically propagation of energy. Let's keep it very simple. Wave is propagation of energy or momentum. So right now if I am talking and somehow you are receiving my sound energy, so like that is energy propagating for you, right? So if we have to give the most basic definition of a wave, then we will just say it is the propagation of energy and momentum, right students? Energy and momentum from one point to another. from one point to another. So now you would say that if I release this pen, that has also transferred energy from this point to this point. No, that is not the case. Bulk movement of particles should not take place. Energy and momentum can be transferred, but students, without bulk movement. Without bulk movement. You know why am I giving it so much of time? Because understanding the basics of waves will definitely give you an edge in understanding all the further units. So without bulk movement of particles. So particles are not moving in bulk. They will only transfer their energy to the next particle, then to the next particle, then to the next particle. Somewhat like how dominoes work. So you flick one domino, it will transfer its energy to the other one, and so on, so on, so on. The energy will get transferred, but you don't need to move yourself to transfer that energy, right, students? So that is what waves are. Wave is basically transfer of energy or transportation of energy or propagation of energy from one point to another point without bulk movement of particles. Please write down, then we move forward. Right, students? So now if you understand what waves are, let's talk about, what is a wave motion. So a wave is a disturbance that transfers energy from one place to another. It does not transfer matter during the energy transfer, right, students? Then wave motion is made up of periodic motion or motion repeated at regular intervals. Now let's talk about that. So when I was talking about waves, I told you that this has an integral role. So what is this kind of a motion? This is oscillatory motion, right, students? So any wave that you see around, whether it be light, whether it be sound, whether it be a water ripple, it is basically a continuation and a repetition of movement. It is basically what? A repetition of movement. So you can also relate with one more wave that you create yourself, that is, let's say, a Mexican wave in the football field. So what happens is, it is just a repeating pattern. Let's say the first person goes up, the second is down right now, then vice versa happen. Now this person will go up, then this person will go up, and so on. So you will get an illusion as if the pattern is moving forward, as something is moving forward. But are you moving forward? You are still on your seat. You are not moving forward. It is just the pattern that moves. So can we call it like this, that wave propagation is basically the propagation of a particular pattern, right? So that is what I have shown here. Let's say you imagine a wave like this, where you have a string tied to one end of the room at one wall, and the other end you have in your hand. Can you create a wave like this by flicking this string up and down? Yes. So what are you doing? You are creating a pattern. This pattern, let's say this pattern created here, the next moment it will be here, the next moment it will be here. You will feel as if the string is moving forward. But is the string actually moving forward? No, it is in your hand. You are not going anywhere. The string is still between these 2 points. But you get an illusion that the string is moving forward. Why? Because the pattern, the next moment it is forward. That is waves for you, right? So wave is a disturbance that transfers energy, and wave motion is made up of periodic motion or motion repeated at regular intervals. Straight away, let's talk about these two versions of waves. First is the transverse wave. Students, please understand, this is called transverse wave and this is called longitudinal waves. Longitudinal waves. So in both the cases, you will feel there is a difference. What is happening in the first case, where the string is being flicked up and down, the particles of the string are moving up and down. You can verify that. You tie a ribbon at a particular point on the string, and when you move it up and down, you will see that ribbon is moving up and down. So particles are only moving up and down, but the pattern is moving in the forward direction. So when the wave is propagating forward, while the particles are moving up and down, then that is transverse wave for you. Now what about longitudinal wave? Imagine a spring and you compress it and leave it. You will see as if these particles are oscillating along this direction, right? And what is happening? The wave is also moving in this direction. So when the wave is moving in the same direction and the particles are oscillating in the same direction as well, then we call it as the longitudinal waves. I will give you one more example which you cannot relate with right now. This is light for you and this is sound. So as I told you, our discussion will be somewhere around light and sound in this unit. So both are of each type. So sound is longitudinal and light is transverse. So when I say longitudinal, what I am doing is I am talking and I am disturbing the air particles. Those air particles are moving forward and not moving forward in bulk, but transferring their energy to the next particle, then that to the next particle, and so on. So this is creation of longitudinal waves, right? So sound is longitudinal wave while light is transverse wave. Okay. So in fact, we also have an idea because of we have studied infrared waves in the previous chapter where we had discussed, electromagnetic wave spectrum. So there we had discussed about microwaves, radio waves, all these kind of waves. So those were all what? Transverse wave. So when we talk about transverse wave, you can see a pattern here. So let's say string was very taut in one direction in straight line and then you started flicking it. So this was the original pattern of the string, but now it is like this. So the particles here are above their rest position. Initially they were all at rest in this particular position. Now the particles here, they are above their mean position. This is called crest. What do we call these, students? Crest. While the particles which are below their mean position, their rest position, this is called trough. Keep that in mind. So crest and trough formation takes place in transverse waves. Okay. What about here? So imagine if I tell you that, this was the situation of particles. Okay, I am making equally spaced particles. Okay, roughly I have made equally spaced particles. Now these particles starts oscillating, right? So in the same direction, here they were oscillating perpendicular, here they are oscillating in the same direction. So let's say this particle moved forward, this particle at the same time moved backwards. So what do you have here? You have three close by particles, right? Since this moved backward and let's say this moved forward, so here you have in a way, less density of particles. So here the particles have come closer because the left particle has moved towards the right particle has moved towards the left. So this creates a compression. This creates a compression, students. All right. So compression is where the particles are closer, the density at this point is more. So this particular situation is called rarefaction. What is it called, students? Rarefaction, where there is a lesser density. So here we had crest and trough formation. Here we have compression and rarefaction formation, right? So how does that happen? Are you understanding? Similarly, now what happens is this particle has moved leftward, this particle has moved rightward. That is why now since this has moved leftward and this has moved rightwards, we are left with only one particle here. So again, this is a rarefaction. Then again, this one moves forward, right? This one moves backward. So we again have what? Closer particles here. So again, this is a compression, and similarly this would be a rarefaction. So when I was not talking, this was the situation of the air particles, but when I start talking, this becomes the new situation. So this is compression and rarefaction. So I hope you are able to understand what are longitudinal waves and what are transverse wave. So how would you define this, students? Transverse wave, you can write, in this wave the particles oscillate perpendicular to the direction of movement of wave, right? So transverse wave, particles vibrate perpendicular to the direction of movement of wave, right? Students, keep writing that. This is a new unit, it will take time. We are willing to do that. We are willing to give it a little extra time because this is something very new for you. Now longitudinal waves, what can we write? Particles vibrate or oscillate, vibrate also, or we can write oscillate along the direction of wave. But again, the bottom line is that no one is moving in bulk. They are all at their position, slightly moving here and there, and are able to propagate a pattern, propagate energy, and propagate momentum. Right. All right, students. So, next thing now is just one more idea that you should have, a very common wave, that is a shock wave that is caused by earthquake. We call them seismic waves. So I don't know if you're aware of this or not. Whenever there is an earthquake, obviously you feel something is moving. So we have an epicenter where there is an origination of earthquake, and then its effect, its ripple effect, is transferred further and further and further. But while that is happening, there are two kinds of waves simultaneously propagating. One is seismic P wave. So P can be treated as primary. Okay, this is basically pressure wave. These are longitudinal. So many times you will have question on this. These are longitudinal, their speed. So when I say wave speed now, even though I have not talked about it yet, but when I say wave speed, that is the speed with which the propagation is happening, right? So the wave speed of longitudinal wave is about 6 km per second. That is for the P wave. So that is going in the form of rarefactions and compressions, as you may see. Okay, and this can travel through all medium: solid, liquid, and gas. This can move through all kinds of medium. These are longitudinal wave. These can move through solid, liquid, as well as gas. So this is the wave that first reaches any point. These travel at a faster rate, while the seismic S waves, that are the shear waves, or you can call them as the secondary waves, they travel with a speed much less than that. So this is like 4 km per second. So they will reach. So are you understanding what you mean by wave speed? So for example, from epicenter, let's say you are hypothetically 300 kilometers away. You are 300 kilometers away. Okay, so if hypothetically the S wave is traveling with 6 km per second, so after how much time will it reach you? Think about it. So the distance is 300 kilometer, the speed is 6 km per second. So 300 divided by 6, that is going to give you what? 50 seconds. So after 50 seconds, you will first feel the effect of an earthquake. That is basically the P wave that is reaching you. What about S wave, students? Again, if you are 300 kilometers away, then divided by 4, then of course it is going to be, it's traveling with 4 km per second. So it will reach you in about 75 seconds. So you will get a double shock in that sense. First you will feel, what you will feel is the P wave, then what you will feel is the S wave. Longitudinal, these are transverse, students. These can only travel through solids. We will discuss why. Because we need rigidity. We need rigidity for these waves to exist. So rigidity is only there in solids. That is why these can only travel through solids. So they will reach later, but they will have more devastating effect, I think. Why? Because these are transverse in nature. These will cause more devastating effect. So hardly any difference, like around 25 seconds the difference is going to be between the P wave and the S wave, right? So primary wave, secondary wave, this is another category of wave which you don't want to encounter for sure, right? So you know what are water waves, you enjoy them, but you don't enjoy these waves, right? Okay, write down and then we move forward. All right. So next is wave representation. Now students, if I have to make you understand this to any of my students, I will give you a very simple idea. Let's say you took the example of a transverse wave. You had tied a string on one wall and the other end of the string is in your hands, and you are moving it up and down, up and down, up and down, and you're creating a pattern that is moving forward. Again, string is not moving, the pattern is moving. Now you are seeing two diagrams here. You would say, why are there two diagrams? So understand, students, this is versus distance. So imagine you click a snapshot of the wave, right? So you are not talking about time here, not talking about time. How, students, how? So when I say we have clicked a picture, so can we see the variation with time? No. this is a picture, this is a photograph. So all we can see is how wave is changing with distance, how wave is changing with distance. So you would say, okay, fine, this is one crest, then this is one trough. Can we say one whole pattern has been accommodated in this? Yes. So this can be treated as one wavelength, as I have written. This can be treated as one wavelength. One whole wave is accommodated in this, right? So you can call this as one wavelength, or what you can do is, you can call this also as one wavelength from here to here. Why, students? The idea is to cover all the particles once, and then it is just a repeating pattern, isn't it? So one wavelength is going to be this also. So sometimes people call it as the distance between two consecutive crests. Can you imagine? This can also be one wavelength. So wavelength means all particles once covered is one wavelength. But the best way of visualizing it is, I think, still this is the best, where you have talked about, starting here and ending here, all the particle, one crest, one trough, this distance. So if this distance is in meter, can you say that the wavelength is 40 meter? Yes. So one crest is extended in 20 meter, then the next trough is extended in another 20 meter, and overall the one wavelength is 40 meter, right? How high the particles are going up and down is basically the amplitude, So this is the amplitude, right? So wavelength, amplitude, can you define them? So amplitude is the distance between the mean position and extreme position of the particle, between mean position and extreme. So can we call them extreme? Yes, they can go up to this, and this is also extreme. Imagine this particle can go from here to here, up and down, up and down. So these are called the extreme positions, and this is called the mean position. This particle is not going forward again, it's only moving up and down. Okay, fine. So what is the amplitude? I'm not making you write this definition. The distance between the mean and the extreme, the maximum distance that particle can move from its rest position, is the amplitude of the particle, right? Or the wave. Next, students, wavelength. You can call it distance between two consecutive crests. You can call it the distance between two consecutive troughs. That is basically the distance in which whole one wave is accommodated, right, students? Next is frequency. Now, time period and wave speed. Okay, so now we will not look at this diagram, and now we will focus on the next diagram. Now you will say, what is this? This is variation with time. This is variation with time. So how can you see variation with time? So just now I was giving you an example. Let's say you fix a ribbon here. Let's say a red ribbon. Okay. Let's say you fix a red ribbon here, and you just keep on, visualizing this ribbon. So this will keep on moving up and down, up and down, up and down. Its amplitude is still going to be the same, right? Amplitude is still going to be the same, and that is how much? So let's say hypothetically this is 10 centimeter. So it will also move up to 10 centimeters, students, right? That is wave for you. You should understand the basic parameters. Now, what is one time period? What is one time period or period of wave? So imagine if I am creating the wave like this, like this, like this. So imagine I start from the rest position. This moves up, then it moves down, and then it comes back to the same point, right? Moves up, moves down, comes back. So the time I take to create one oscillation, that is one time period. So imagine when I have created one whole oscillation, the wave has propagated exactly one wavelength, isn't it? So when I do this, one crest has formed. When I do this, one trough has formed. So when I do this whole, one wave has formed. So the time it takes to make this whole 40 meter disturbance move, that is basically 4 seconds. That is basically 4 seconds, one oscillation. So what is time period, students? The time taken to complete one oscillation or one wave. Time taken to complete one wave. Can we call it like that? Yes. We can also call it as time taken to complete one oscillation by the particle. So hypothetically, if it is 4 seconds here, so can we say what is the wave speed now? So it took me 4 seconds to do this. So it took 4 seconds for one wave to form, isn't it? So can we say that wave speed, what is it students? Wave speed is basically the speed of propagation. What is it? Speed of propagation of the disturbance of the, is it the speed of the particles? No. Particles are moving up and down, up and down. It is not their speed. It is the speed with which the disturbance is propagating. I give you a brief here. So for example, if I have to talk about the speed, so how much has wave traveled? 40 meter. In what time? 4 seconds, isn't it? So wave speed is nothing but 40 over 4. That is 10 meter per second. So the wave is propagating, the disturbance is propagating at 10 meter per second, right students? Can you visualize it like this? So this distance, one wavelength, we denote it by lambda students. There is a symbol for this, lambda, we call it lambda. Okay, so this lambda is equal to the one wavelength and this is one time period. So can we call the wave speed v as lambda over t? Of course, distance over time. So distance, the distance that wave has traveled is lambda and the time it took for that to happen is 4 seconds. So can we call it as lambda over t? Yes, of course. So now what is frequency then? What is frequency? So imagine this time period would have been 0.2 seconds. How much students? 0.2 seconds. So what do you mean by that? In 0.2 seconds, one wave is created. So how many waves will I create in 1 second? Think about it. 0.2, 0.2, 0.2, 0.2 and 0.2, 5 waves. So basically frequency, we denote it by f, is the number of waves passing a point per second. I have purposely not straight away written the definitions for you. I will share those slides with you in which the definitions are there, the notes will be shared with you. You have to understand why are we writing the definition in this fashion. So number of waves passing a point per unit time. Per unit time. So we can call it per second, right? So if I tell you the time period is 0.2 seconds, so what will be the frequency? You will say 5 in 1 second. How many waves have been created? 5. What should be the unit? So unit we call it as hertz. After the scientists who contributed in this direction, we call it hertz. So frequency is 5 hertz, 5 cycles per second, 5 waves per second. We call it as hertz. So can you relate the two? Of course, you should be able to do it. So F is equals to nothing but 1 by T. You want me to take one more example? Let's do that. Let's say time period is 0.25 seconds. So how many waves will be there in 1 second? 0.25, 0.25, 0.25, 0.25, 4. So can we say that frequency is going to be 1 over time period? That is 1 over 0.25. So that is going to be 4 hertz. Right students? So can you rewrite this now? Of course you can. 1 by T. Can I write this as 1 by T? And what is 1 by T? F. So V is equals to F into lambda. This is the main expression students on this slide that you're seeing. This is the most important thing, that V is equals to F lambda, where V is the speed with which wave is propagating, F is the frequency and lambda is the wavelength. So have I covered all 5? Are you able to understand all 5 now? Amplitude, yes, the extension of wave in this direction, in what amount the particles are going up and down or back and forth about their mean position. So that's majorly about particles displacement. Wavelength is like length in which one whole wave, the empirical wave, is completed. Frequency, number of waves per unit time. Then is time period, time taken to complete one wave. And wave speed, the speed with which the disturbance is propagating. What is it equal to? F lambda. Write everything that you have on the screen, then we move forward. So the wave speed here is F lambda. Can you tell me what is the frequency here? So frequency here is going to be 1 by T. So that is rather going to be 1 by 4. Right. So frequency is 0.25 hertz. So it is only 0.25 wave created per second. That is why it takes 4 seconds to complete one wave. So can we verify this formula now? V is equals to F lambda. F is 1 by 4 or 0.25. Right students? F is 0.25, and what is lambda? So lambda is 40, so this is giving me 10 meter per second. You can verify that yourself, then we move forward. Alright students, so now let's do a couple of questions. Figure shows a displacement distance graph. So this is displacement distance graph, students. This is like clicking a picture. You cannot extract the information of time in this. Okay, so you would ask, what is this graph then? So you can call it like observing this red ribbon and making a video of it. So then when you are making a video of it, then you are basically observing the variation with time. But when you click a picture, you do not see the variation with time. Okay, sorry. So students, figure shows a distance versus displacement versus distance graph of a wave. What is the wavelength of the wave? Can't get easier than this, students. So let's say this is the starting point of the crest. So like the top of the crest, then this is also the top of the crest. So this is like 50. So the wave is extended in 50 and the unit is centimeter. So the wavelength of the wave is going to be 50 centimeter or 0.5 meter. Next, the period of the wave is 1.0 second. What are its frequency and speed? Right. So frequency is 1 over t. So that is going to be 1 hertz. Since it takes 1 second to complete one wave, it is like 1 wave per second, right? And what about the speed? So v is equals to what? F lambda. Now f is 1 and lambda is 0.5. Be careful, 0.5 unit should be meter per second, right? Then what will be its wavelength? What will be the wavelength of the wave? If its frequency is increased to 5 hertz with no change in speed. So now the next part, student, C part, the new frequency has been made. Let's call it f bar, f dash, whatever you want to call it, as 5 hertz. But the speed is still the same, right? Speed is still 0.5. So what will be its new wavelength? So can we write, since we know that, you know, v is equals to f lambda, that's our formula. So lambda is going to be v by f, v is going to be 0.5 and f is like 5. So lambda is like 0.1 meter or 10 centimeter. Okay. So now if instead of 50 centimeter, the wavelength has become what? 10. So can you visualize this, students? Let's do that. Let's try and understand what has happened here. So let me draw that for you. Okay. So let's say if this was the wave. I'm drawing one pattern. Okay. So if it was like, this is the amplitude, that is still 5. The amplitude is 5, students, it's somewhere in between 4 and 6. But now, even if we start with this and let's say we are going the corresponding point, that is 50 in centimeter, right? Distance in centimeter. Right, students? What you have to do is accommodate 5 waves now. So it could be like this, 1, 2, 3, 4, 5, somewhat like this. You will try and accommodate. So this is like 1 wave, this is like 2 wave, this is like 3 wave, this is like 4 wave, but we need 5. We need 5, students. We need to, you know, erase this and try to make it 5. So I will try and do that. Let's see if I will be able to do it. 1 wave, 2 wave, 3 wave, 4 wave, 5 wave, somewhat like this. 1, 2, 3. So let me do it. Let's not draw it to the scale then. 5. So I should draw this within 50. Within 50, I will have to make 5 waves now, right? So if it was 1 wave in 50, now it will need to be 5 waves in 50. Why? Because the wavelength has been squeezed. It has been squeezed to 10 centimeter, right? So if in 50 centimeter we had 1 wave, now in 50 centimeter we will have 5 waves. I hope you understand that. Sketch the resulting wave profile with its wavelength marked clearly. So now the wavelength is going to be only this much, students, that is 10 centimeter. That is going to be 10 centimeter, right? So this is again distance. You can follow the same pattern, distance in centimeter, and this is again distance in centimeter. I hope you are able to understand, students, and you are understanding how waves are. I am only giving you the basic mathematics today, and next class we will start relating it with sound and light then. Okay, now you want to try it one question yourself, you can do that. So figure shows the distance versus displacement graph and a distance displacement versus time graph, right students? So this time it's displacement versus distance and displacement versus time. So both the versions as we had discussed. State the amplitude of the wave. So there's no doubt about it, amplitude is 0.6 meter. State the wavelength of the wave. So will this give us the wavelength or this? This one, this is not going to give us the wavelength. So what is one wavelength? So this is 5 meter. 5 meter. State the time taken for one complete oscillation. So this is giving us the time. So how much is this? So this is 2.5. So this is like 1, 2, 3, 4. So in 4 we have like 2.5. So what is 1 equal to? So this is like 2. What is one block equal to in seconds? So 2.5 divided by 4. Isn't it student? 2.5 divided by 4. So that is going to be how much? So this is going to be 0.5. Let's divide 2.5 by 4 in fact by a calculator itself. 2.5 divided by 4. So that is 0.625. So one block is 0.625 seconds, right? So how much will be one wavelength? 2 blocks, right? So sorry, one time period, 2 blocks. So multiplied by 2. So when we multiply it by 2, we get 1.25, right students? So or we can do it like that simply, that there are 2 waves. Can you realize students, there are 2 waves in 2.5 seconds. So one wave will be 1.25 seconds. Any which way you can do it. So time taken for one complete oscillation, the answer should be 1.25 second. Calculate the frequency of the wave students. Of course you understand that frequency is going to be 1 over the time period. So frequency is 1 over t. So that is going to be 1 over 1.25. That's going to be 4 by 5. So that's going to be 0.8 hertz. Right students? Don't worry if it is less than 1. That can obviously happen. That means within 1 second you don't have one complete wave also. Okay. Right students, I hope you are able to understand and keep up the energy. Calculate the speed of the wave. Now it's your call. I think we should go with f lambda. F is how much? It's 0.8 and lambda was how much? So it was 5. So this is going to be 5 times 8, that is 4. So this is going to be 4.0 meter per second, right students? I hope your answers matches with mine. You always have to do that. Try the question yourself, then go for the solution. Right students, next, very quickly, then wave front. Okay, so I will not give you much time here, just understand this. What do you mean by a wave front? So, or what we can do is like, we can end this class here, and then in the next class what we can do is discuss wave front and water waves. So let's keep it like that. First we are discussing about what? The general properties of wave. Next we will discuss water waves in a short video. Then we will talk about sound. Then we will talk about light and so on. But let's keep it to what do you mean by waves and the general characteristics of waves. There are various types. We will talk about them one by one. Right students? So I hope you were able to understand whatever I had taught you today, and you should be able to apply it. Very next video we are coming up with the concept of water waves, right? Water ripple. Alright students, keep working hard, keep making your parents proud, and I will see you very soon next time. And do let us know what all topics you want us to cover as soon as possible, which can help you achieve the desired result. And as usual, once we complete the unit, we'll come up with the previous year questions of this particular unit, right students? So that's all for this one. I'll take your leave and I will see you very soon next time. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.